Yeah, so welcome to our next session. Without further ado, I will hand over to Fulvio for non-diffusive particle transport.
Right, so good morning, everybody. Let me start by acknowledging my co-authors of this talk, and also by thanking the organizers of the Festival of Théorie. It's been 20 years exactly since I gave my last talk in this audience, and time really flies. Time is not the only thing that flies, also filaments in the escape layer, plasma filaments in the escape layer of fusion machines, which is the subject of my talk today. So let me give you a bit of context before I get into the math and physics. I'm going to talk about the physics of the boundary plasma in fusion devices. And fusion machines are fundamentally nonlinear open thermodynamic systems out of equilibrium, which sounds very cool, and it actually is. But what that means, considering the fact that they are open systems, is that they leak. We try to confine our plasma to make it hot and dense, because that's what we need to do in order to get efficient fusion reactions. But unavoidably, we also have energy and particles that are leaking out from the well-confined region. And this has a number of effects, because the stellar temperature of the plasma meets the earthly environment of the walls of the machine. And this interaction is, I would say, complicated. It's complicated because it implies that the plasma erodes the plasma-facing components. And by doing that, it limits the lifetime of the internal walls. This is a major problem for fusion engineers and fusion physicists, because the lifetime of the components also determines the cost of electricity. We really care about that as well in the prospect of having commercial fusion. It can affect the overall performance of the machine, because the only material then goes into the plasma and changes its behavior. And it can even lead to destructive damages, which will really affect the capital investment of several billions that people put into a future power plant. So the problem here, the problem that I will be talking about, is a particle transport in the boundary region of the escape layer. You can see here a nice simulation that one of my postdocs did a couple of years ago of Must Upgrade, the machine that we have in the UK. And you can see how nice it is. I mean, it does move. I don't know if you can see that, but there are filaments that are moving in the boundary region of the machine. And this is a very complicated simulation. It takes a long time, yes?
This is the picture of magnetic field?
No, this is the picture of vorticity in the boundary region of the plasma. It's the same vorticity that David was talking about earlier. And so, but you can see that there are vertical structures, like filaments. You can see them wrapping around the machine. And this is fundamentally a quanta of transport in the boundary region of fusion devices. But these simulations are very complex. They take a long time to set up, and an even longer time to get to saturation, when they get to saturation. So it's extremely complex to design power plants using these kind of tools, although that would be the dream. They're very accurate, very useful to understand the physics, but very impractical when it comes to do very large scans of parameters to understand which is the best engineering solution for a power plant. And we really care about that. So what we want is to have quick and accurate tools. And in order to get quick and accurate tools, we need to have understanding, hence theory. What we want to do is also to have simplified models that can somehow bypass the complexity of these simulations while still capturing their accuracy. And having these tools would be really important to assess erosion, the capabilities of pumping the plasma and the helium ashes, understanding the access to detachment, which is needed to prevent the machine from melting, and for many other reasons. Okay, so here you got a picture of Must Upgrade inside. This is a typical machine. I use Must Upgrade because it's our own toy, but you would see something similar in all the different devices around the world. And on top of this picture, you see also the magnetic field, specifically the separatrix that separates the well-confined plasma core inside here and the boundary region, which is just out here, which is in contact with the surface eventually. So the interesting thing here is that the transport that causes the plasma to leak out, which is the subject of this talk, is fundamentally driven by turbulence. But it's a pretty peculiar turbulence, also quite different from what we see in the core. We are so lucky that we can actually see this turbulence by the naked eye. If we had a window, and we do have windows in machines, this is what we would see. It's a lot of filaments, plasma filaments, I'll play it again, that are erupting from the surface of the machine. A lot of questions, yes.
Is that a simulation or
No, this is a real picture of the plasma turbulence in the machine.
And how is the magnetic field detected?
This is not magnetic field. This is a light. This is light as you would see it with your eyes. So this is visible light. It's light emission caused by the fact that the plasma interacts with neutral particles that are present in the boundary region of the machine. And this is fundamentally a glorified neon light. It's exactly the same mechanism. This movie is actually slowed down significantly because the discharge is typically of the order of 1 second. It must upgrade. But if you slow it down using just a visual camera, okay, they're very sophisticated CCD cameras, but they're no different from what you have on your phone. You would see this. You would actually see this.
Thank you.
Okay, so as you can see, there are structures that are moving around in the boundary region of the plasma. We can see them and we can analyze them. And the filamentation of the plasma is a typical phenomenon. It happens also in many other situations, so physical situations, and it's fundamentally due to the symmetry of an anisotropy that is caused by the magnetic field. Along the field lines, the plasma moves easily. Across the field lines, the plasma does not move easily. Hence, it creates filaments. Okay, so one interesting feature of this turbulence is that it's non-local. And we know it's non-local because we take measurements of particle fluxes and gradients, and we can try to match our observation with a fixed law approach. So relating the flux with a gradient of the density, for example, or we can extend it also having an advective term. And if this relation, a standard local relation, was holding, we would have just a straight line in this diagram. These are experimental data. I will not tell exactly how we calculated these objects, but it's pretty straightforward, and you can see it here. But if you had a local advective diffusive behavior in the boundary region of the plasma, you see here a straight line. This is a scatter plot. It's really not a straight line. These are experimental data, and what this suggests is that the behavior of the plasma turbulence is non-local. We see this also in simulations, by the way. It's not only an experimental observation. And a hint of this is that we have coherent structures that are moving in the plasma. And this suggests that there is some non-local effect. Yes, another question.
You mean non-local in physical space?
Yes, I will say non-local in physical space. So when it's in physical space, I will say non-local. When it's in time, I will say that we have memory effects.
Something that can only be represented as a kernel, but not as a differential operator.
Well, let me get into the discussion later, and you will see all the details, because I will address exactly what you're saying.
Yes, a relevant question. You mean non-local and non-sequential?
Okay, I mean non-local. Non-local.
Yeah, just because we are already in the discussion phase.
Yes, exactly.
Yeah. So you might have the density gradient, but of course you can have the diffusion coefficient, but there will be diffusion stuff. So
yeah,
because it's not taking into account,
yeah,
I guess it's
yeah.
Yeah.
Yeah, no, of course you can have also non-diagonal terms that affect the behavior of the plasma. But I think that there are also more intuitive reasons why we could see that the turbulence in this plane is really not local. Okay, so this is a bit of the outline of the talk. So this was just introduction, a lot of questions already. I will start by describing a statistical framework that we developed a few years ago. Then I will mention how the filaments are moving, and this has a direct consequence on the framework, the statistical framework. Then I will mention how we could build fractional derivative models based on the physics that I've discussed. And finally, I will try to describe how we can do this with first principles. Okay, let me start with the statistical framework. There is a bit of math here, but hopefully it's also quite intuitive. The idea here is that we want to treat individual filaments as separated objects that are not interacting with each other. And there is a good evidence, both experimentally, numerically, and theoretically, that the filaments are not very strongly interacting in the context of the boundary plasma. And so we take these individual filaments and we describe them as fields in a 2D plot. And this 2D plot is fundamentally in a 2D space. And this 2D space could be imagined as a plane that is basically the midplane of the machine. And the filament crossing this plane would be represented by a footprint, which could be, for example, a Gaussian footprint. And this Gaussian footprint we can represent with a field by saying it depends on the radial direction, the toroidal direction, and time. This eta could be density, temperature, whatever other thermodynamic variable. For the moment, I would encourage you to think of it as a density. And this density has an initial amplitude. It's lost outside this plane by the fact that the filament will propagate in the parallel direction along the field lines. So these filaments are typically aligned with field lines. And then it has a shape, which I assume is maintained as the filament moves radially and toroidally with a certain velocity. And each filament has a different size delta. Okay, so we do that. And then the next thing we do is to think, yes,
Sorry,
I will never finish like that.
absolutely. But are those filaments the solution of your MHD or some kind of fundamental equations?
No, for the moment, it's something that I impose based on the fact that I do observe them. I see filaments happening in the scape layer. I know that when I put a chunk of plasma on open field lines, it will tend to elongate very quickly because parallel transport is faster than perpendicular transport. And now here, I'm trying to model this by saying that a filament would have a certain field that I represent with this mathematical architecture.
But the function you choose doesn't need to be a solution of your determining equation.
It could be, but it doesn't have to be.
But you don't choose it to be.
No, I don't choose it to be. Because in the context of this framework, I can maintain some flexibility. But you have the flexibility of choosing it the way you want. Okay, so once I choose this shape, I can then say that in a period delta t, arbitrary period delta t of observation, I got a number of filaments, k, that combine to create a more complex field. So as you can see here, I got my filament moving. This is an individual filament in 3 different times. Here it's the same time, many filaments together launched in a random way, again, in a non-independent way. So I sum up the individual filament fields. Each filament leaves the separatrix, which we assume is going to be here at a time tau 0 I. And then if I build the system in this way, I built fundamentally a shot noise, a so-called shot noise, which is a statistical noise that can be found on textbooks. And the way I constructed the thing, I created fundamentally a Poisson process. Again, statistics, if you're not familiar with that, just trust me, this is the way it is. Once I do this, I can then say, okay, I got my full field, but I really care about a single toroidal location, which is what I do when I took measurements in an actual machine. And so I just focus on an individual toroidal position, a certain value of y, which I call y star. And then I integrate over time because I want to get to a profile rather than having an instantaneous realization of my field. Next, by construction, this framework that you're constructing is ergodic. And so I can replace the time averages that I had before to construct the profiles with ensemble averages. So I need to have the statistics of the amplitudes of the filaments, the statistics of the size of the filaments, the statistics of the initial positions of the filaments, the statistics of the waiting times of the filaments. And I can replace my time integration with this ensemble integration. All this can be rigorously demonstrated. I will not do that, but it's the way it is. Then I can take a limit of an infinite observation time and using some nice statistical properties for shot noise and Poisson processes, I can get to the point of creating a radial profile of my thermodynamic variables. Again, in this case, we can think it's a density. So you can also see it here. I got all my filaments moving. This is completely random, and I'm launching these filaments as if they were with a certain shape and velocity that I impose. But I can impose it. I can choose these things based on what I observe in my simulations of my experiments. Then I can just observe what is happening along these lines. And what is happening is this instantaneous profile that changes continuously. I can then average it and get this green profile, which is my density profile on a coarse time scale. And if I have a probe over here, I will see this kind of behavior, which is actually what we see in experiments. Okay, fine. So now the nice thing here is that by just having information on the profiles of the, sorry, not the profiles, on the filaments, individual filaments, so how they are statistically distributed and how they move and what the shape is. So if I have a mesoscopic final representation of my system, I can then get to a macroscopic representation, which is coarse in time. So these would be the profiles. Yes, question.
Yeah, so I think right, each of these terms is a product distribution.
Yeah.
Somehow you're assuming that each of these processes are independent.
Yes.
Whereas in reality, what scientists think that
Yeah.
all these things are related to each other. So if there is motivation physically to assume that
Yeah.
all these narrowly look independent what are actually.
So let me see if I understand your question. I could interpret your question as the filaments are independent from each other. It seems like they are. We've been looking at that. We've been launching filaments in simulations at different distances from each other. And we see that only when they're very close to each other, they actually interact. And looking at the filaments from these images over there, we can estimate what is the average distance between filaments. And it's larger than their interaction distance. You can do that, and we've done it. We've got papers on this. So we can assume that the filaments are independent from each other. It's not perfect, but nearly okay. Or you could say that these quantities, average amplitude, sorry, not average amplitude, distribution of amplitude, distribution of size, this could be collinear. They don't seem to be. We take these as an input, this probability distribution as an input, based either on simulations or observations. But yeah, there could be some collinearity in principle in statistics. That is part of the story that we do not address. Okay, in any case, the idea is that I can construct fundamentally an integral operator represented by these brackets that takes the information on the filaments and translates it into profiles. Interestingly, I can do the same thing also to get the fluxes. So this framework allows you also to calculate the particle fluxes or the thermodynamic fluxes. With this information, I could in principle build effective diffusion and velocity coefficients, which is what many codes use in our community, and feed them into the codes to have maybe a better representation of almost a principal representation of how the turbulence should behave or the profile should behave. But I don't like that because I do think it's actually quite wrong because structurally this equation is not the right one to put into the codes. I could alternatively assume that I have a nonlinear non-local model represented by some sort of a non-local kernel. And having this kind of representation and knowing that I can go from my filament properties to these profiles, I can build the Fourier transform on my non-local kernel. So I can calculate that. And that can give me information on how non-locality plays in this problem. The inputs of all these are the filament statistics, and that is something that I have to get from somewhere. It could be a very smart theoretician that tells me how the turbulence behaves in the core, because this turbulence is imported from the core. It could be because I just observe it, I measure it in experiments, and we've done that. We have measured these PDFs. Could be because of simulations that are looking at that specifically. But the interesting thing is that all these statistics is coming from the core. So I'm looking at the region outside the set of things. And if I know how things are ejected, then I'm good. Then I can take the region from the separatrix to the wall, and I have all the information that I need. But I also need to understand the filament dynamics. So I'll talk about filament dynamics a little bit here. Okay, so filament dynamics has been studied for many years. There is a classic paper in 2001 by Sergei Krasheninnikov described how filaments are moving. The idea is that you have a filament of plasma. Fundamentally, it's a pressure perturbation in an environment in which there is very little pressure. And what happens here when you have a magnetic field that is changing in the radial direction, because we have a toroidal magnetic field, is that the ions and the electrons get separated because of curvature drifts. One species goes up, the other species goes down. This charge separation creates an electric field. And this electric field is fundamentally propelling the particles through an electron speed motion. So this is a pretty simple and intuitive picture, but I never really liked it. It's correct, it's perfectly correct, and it holds. But in my personal opinion, and many other people might disagree, it's not as elegant as it could be because it mixes a particle and fluid drifts in a way that is maybe not completely clear. It doesn't take into account the effect of currents that might arise in the filament. Of course, if you have charge separation, then you have to derive current somewhere. Other models do that, but not this one by Krashenikov. And it does not, in my opinion, produce a coherent picture that can then be extended to more physical effects. So what I did a few years ago was to try to make this picture a little bit more coherent. It's not going to be better than the one that Krashenikov has. I think it's better from the physical point of view, but maybe it's just a personal opinion. And this is based on buoyancy, magnetic buoyancy. So Archimedes already 2,500 years ago told us that if you put a ball in water against gravity, it will tend to go up. There will be a buoyancy force. In the presence of filaments, we have something similar. Gravity is replaced by the curvature of magnetic field, which effectively acts as a pseudo-gravity. And the filaments are pressure perturbation with respect to an environment that we have in the system. But there is a major difference. The plasma goes, the ball goes against gravity, and the filament goes against the curvature magnetic field. But in the case of the ball, we have a density inside the ball that is smaller than the water, its environment. And in the case of the filament, it's the other way around. So how do we explain that? Especially because there is a complete symmetry with respect to the neutral fluid and the plasma. Well, we explain that by the fact that in reality, what matters here is the magnetic pressure, not the kinetic pressure. And in the filament, we have the magnetic effect. So whenever you have a pressure perturbation, you tend to expel the magnetic field. This expulsion of the magnetic field makes the magnetic field in the filament lower than its surroundings. And since the magnetic field is actually dominant over the pressure perturbation, this means that the filament is moving towards the outer walls of the machine. So very simple explanation, but we can go beyond. We can basically say that this is the force that is acting on our filament. And if we integrate over a certain volume, we look at the force acting on this plasma element. Then we can observe that this equation has a certain equilibrium. And using this diamagnetic correction of the magnetic field, we can connect the variation of the magnetic field with the variation of the pressure that we have in the filament. So we have a nice simple expression. This is making the thing a little bit more spatial. It's a special case, but it is representative. And so what we can do is to put the equilibrium in this observation of the diamagnetic effects into the force that we have on the filament. And with a little bit of algebra, and assuming that we have a large aspect ratio, so a big torus with a large aspect ratio, and we have low beta, so the pressure is less important in magnetic field, we find that this force separates out into two pieces. One is an interchange term that depends on the equilibrium curvature and the pressure gradient in the filament. And the other one is fundamentally sorry, there we go. And the other one is a field line bending term that is due to the fact that we are changing the curvature of magnetic field when we have currents. Again, this term is a little bit more particular and needs to be taken with a bit of care. Okay, so what we can then do once we have our force in the form that I showed before is to do some scalings and balancing the terms in Newton's second law. F is equals to ma fundamentally. So this is the inertial term, ma, and this is the force that I've been discussing so far. So this is going to be the drive term for filaments. There is always going to be a pressure perturbation. This is what defines the filament itself. So this, and there is always a curvature in our fusion machines. So this term is always active and always driving the motion of the filament. The other two terms are important depending on the size of the filament. When the filaments are tiny, the inertial term is important. When the filaments are large, the field line bending term is a dominant one. And you can balance these two terms out and see when they matter. And it turns out it's depending fundamentally on the size of the filament. Okay, Then what we can do is to go and look at asymptotic regimes. When I have a small filaments, I just balance these two terms out, the inertia and the drive interchange term, and I find an expression that tells me how the velocity of the filament, which was an essential element in the statistical framework, depends on plasma quantities, the sound speed, the curvature, and the size of the filament itself. Typically, this is really subsonic. We have velocities that are a fraction of the sound speed. You can see it also here in this plot, which I'll comment in a second. When you have larger filaments, you balance the other two terms, and you come up with a slightly different expression. And with this expression, one key point is to understand how you induce the change in the curvature in the filament of the magnetic field lines. And this change in curvature, I'll get there in a second, finish the thought, is due to the currents that are flowing in the filament itself. These currents can be evaluated using Ohm's law, and you can look at the bulk resistivity of the filament, which tends to be typically pretty low, and the resistivity that you have when you connect to the surface of the machine, where you have a sheath resistivity. You form a device sheath, in that sheath you have a strong resistivity, typically that dominates. Putting all these elements together, you can calculate your variation of curvature, and with this variation of curvature, you can calculate the velocity. Again, deeply subsonic. Yes, there was a question.
Just, I may not have followed. What is delta and what is kappa?
Kappa EQ is the curvature of the magnetic field, typically going like 1 over capital R, where capital R is the major radius of the torus.
Delta?
And delta P or delta kappa?
No, the delta in the U expression. Kappa EQ.
Ah, small delta, this one here.
Yes.
It's the size of the filament. So the perpendicular size of the filament. Yeah. Imagine the radius of those. Yeah. Okay, so if you put everything, yeah. I'll speed it up. In any case, putting these two, putting these two regimes together, you can see them here. This is for small filaments. This is for large filaments. You can also have a Paddy approximation. There we go, larger filaments, small filaments. I won't go into the interactions. You can have a Paddy approximation. You can calculate it analytically. And this approximation, despite the fact that this is a very simple approach, is very good because you can see here with these science stars. Can you see them? Maybe not. You can see them maybe over there. Otherwise, just look at the crosses. We do see numerically that isolated filaments are behaving like that. Now, this is not something that we discovered with this model that I'm presenting. With this interpretation, people knew about that already in the past, several years ago. But again, I think that the framework that we have developed by looking at the forces on the filament can allow also for potential extrapolations and more effects. For example, the effect of interactions between filaments, even if they're small, maybe they can have a role. And this kind of framework can allow you to take that into account. Okay, now let me move to the fractional derivative model. And here, the idea, we're changing pace a little bit. So far, I spoke about the statistical framework. I told you that an ingredient is the velocity of the filaments, and I told you how we can calculate the velocity of the filaments. Now I'm going in a slightly different direction. And then the two things will combine at the very end. What I'm telling you now is that the transport properties of a system can be described by a so-called jump function. And this kind of concept was introduced already by Einstein in 1905 when he was talking about diffusion. So if you know how at different times and at different positions, the particles will jump to a specific position in time and space, you have fundamentally the full information of your system in terms of transport. So if you can map this so-called jump function that maps this behavior, you're basically done. You got the whole information in the system, then you just need to turn it into equations, but the information is there. Now, this is represented by this expression that I have over here. A thermodynamic variable, I call it theta. Think of it as density. At a certain position x, we can assume it's a 1D system, but it could be a 3D system, and a certain time t is fundamentally related to the same thermodynamic quantity at a different position at a different time, multiplied by the probability that the particles associated with this position in time and space will then connect with the new position in space and time. So this is, again, it's pretty standard. And the jump function that I was mentioning earlier is this probability here. That is telling me how likely it is, for example, that a particle jumps a certain distance in certain time. Having this, I can Taylor expand this function, but I don't need to assume that delta x and delta t, these jumps are small. I can just Taylor expand and keep all the terms, so I don't truncate them, and I get this expression over here. And then once I have this expression, you can see that I have derivatives now in space and in time of the original thermodynamic function. So if I rewrite these exactly, I end up having an equation that is pretty familiar to us. ddt of a certain thermodynamic quantity is equals to advection, diffusion, plus an infinite number of other terms in principle. And this infinite number of terms could be neglected as long as the jump function that multiplies these terms in a complicated way, as you can see here for advection and diffusion, is sufficiently small. Not small, is such that the coefficient is sufficiently small. So for example, if you plug in a Gaussian jump function, you end up finding that you're actually left only with local effects. You just see diffusion and you just see advection. But if you have a heavy tail distribution for your jump function, so you have a larger probability than Gaussian to do very long jumps, for example, in a Levy distribution, you would end up keeping all the terms. And keeping all the terms fundamentally means having information that is non-local in space, and you would end up having memory effects if the coefficients associated with time are non-negligible. Okay, so given this framework, what we did with my student Theo in the last few years was to try to calculate the jump function in different systems. So you can see here an Hasegawa-Wakatani-like turbulence and in 2D, and here also in 2D, turbulence that can interchange turbulence that can develop in a situation that is similar to what happens just inside the separatrix, it will be here, and just outside the separatrix, simulating the boundary region of the plasma. So you have filaments that are emerging and then they are moving into the boundary region in contact with the wall. So we've used the tracer particles. We launched on these turbulence simulations. So we did the turbulence simulations. Then we launched tracer particles. We looked at how they were moving, and looking at their jumps, we calculated the jump function. What we did then was to try to fit these jump functions with known expressions, and we did this in Fourier space. Now, for lack of time, I will just skip this, but fundamentally, we were looking at how to transform the jump function to Fourier space and then comparing these with our simulations. One interesting thing is that we used as a fitting functions Levy alpha stable distributions, which are fundamentally a generalization of Gaussian functions. And for the Hasegawa-Wakatani system here, you can see in blue the jump functions that we obtained in the simulations with the tracer particles, and in red the fitting that we have used. And as we increase the C parameter that was discussed the other day previously in a talk, we go from a case in which we do not have zonal flows, fundamentally in a case where we have zonal flows, and the distribution of the jump function changes quite significantly. And we end up having much heavier tails. Okay, one nice thing about the Levy alpha distributions is that fundamentally you can expand them, and expanding them as exponentials, you end up with an expression that includes kappa, the wave number of your jump function, to the exponent alpha, where alpha is not necessarily an integer. If alpha is 2, you got a Gaussian. If alpha is different from 2, you got a generalized Levy alpha distribution. Now, if you replace this expansion in the expression that I had above in Fourier space for my evolution of my thermodynamic variable, you can find that you have terms that are proportional to kappa to the alpha. these terms in Fourier space, when transformed back into real space, become fractional derivatives. There is a fractional derivative as exactly the property that the inverse Fourier transform of a quantity times kappa to the alpha is a fractional derivative. Fractional derivatives are integral differential operators, which includes both integrals and differentials. And the integral part gives you the memory or non-local effect. And with that, I mean the fact that you need to have information over a large fraction of the profile, if not all the profile, in order to understand a local property of the system. So by doing this, we fundamentally used the fits that we got from our simulations, from the tracer particle method, and we built a fractional differential equation. This is a so-called reduced model. It's much simpler than what we started from, at least at first sight, and we can solve it. And this solution is much faster than doing the full turbulence simulation. So we did that using the jump functions that I showed before. And you can see here in this figure, in blue, the profile of density in the direct numerical simulation. So this is the full thing, which took a long time. And in orange, the solution of the fractional differential equation that was constructed using the jump function based on the tracer particle method. So this is a pretty decent fit within the arrow bars, which you cannot see because they are just shaded. Maybe you can see them there. And the idea here is that you can solve this in minutes instead of solving it in hours or days.
There are more people trying to disrupt. Is it faster to do this than to solve the original equation for theta? No, original equation, like the jump function distribution equation with the PDS you have. From the fitting. So still faster. So
I mean, is the question whether in order to solve this problem you need to get the fit, in order to get the fit you need to get to the
It's making the assumption that these are such similar distributions. Does it help in terms of, because I could do the continuous random problem and just solve the original with the original kernels, with the original functions, because you wrote an equation for theta before without making the fractional assumption.
Okay, I understand what you mean. You mean in the statistical framework? Probably yes, but I'm thinking in terms of codes, how to put these in integrated modeling codes that solve many different things in the plasma, including the boundary region. And in those codes, I think this would be the viable way of doing it, by using fractional differential equations. Otherwise, you will need to have plugs in. It might not take into account of other effects. Okay, final slide is a first attempt, again, Cabot, first attempt of looking at the first principle jump function, because so far, what we've done was to do simulations to calculate jump function and then building the reduced model. But we would like to have a first principle jump function that comes only from theoretical considerations. So what we've done was basically to look at the flux, stochastic flux that is generated by having a jump function approach. And we can correlate the particle flux with the jump function. We have an expression, which is this one here, that does that. And if you have this, we can Fourier transform it, and we get this expression down here. And then we can also Fourier transform the gradient of the thermodynamic variable, which is something that we do down here. And these two expressions together give you the Fourier transform of the non-local kernel that we were discussing at the very beginning. So now we're going back to the stochastic framework, because the stochastic framework already gives you an expression for this. So the logic here is, if I want to build my fractional differential equations, I need a jump function. In order to get a jump function, I can use my statistical framework, and fundamentally, I can calculate through the statistical framework the kernel of the non-local transport just by knowing the statistics and the dynamics of the filaments. The dynamics I already know. I have a theoretical model. The statistics is still missing, so it's not completely first principle, but it's as first principle as it gets for the moment, because in any case, you will still need to tell as an input how frequently you get filaments coming out, how big they are, which is their distribution. So this is an attempt at connecting the two lines of research in a way that makes it a little bit more self-consistent. So just to conclude, particle exhaust is a critical design driver for fusion machines. It's absolutely essential. We want to have models that are simplified and quicker to solve, and that can be used also in integrated modeling contexts. They have to be as simple as possible. Direct numerical simulations do not achieve that. And the non-diffusive nature of the boundary turbulence makes everything a little bit more complicated. So fundamentally, we built this non-local kernel using the statistical framework. And with that, we can construct a jump function. And with that jump function, we can build a fractional differential model. And with that, I will stop.